Hello everyone, welcome to the third lecture of this fifth week of the course on measurement and instrumentation, and we are discussing our second module on analog meters, and essentially this is the 18th lecture in this second module. We have been discussing about various analog meters in this module, and in the series today we are going to discuss a new kind of instrument which is induction instruments. And by the end of this lecture we will see that these induction instruments are very much essential to measure AC currents or AC voltages, and we will see that the application of these induction instruments are mostly in the energy meters and power meters, and based on this maybe in the subsequent lectures we may see energy meters specifically based on the induction instruments. So, let us see the details of induction instruments. Okay. Induction type instruments are a class of electromechanical measuring instruments that are used only for the AC current, as I have mentioned. Okay. They are extensively used in the power system measurement for measurement of multiple power related things like power itself, other things like energy, frequencies, or even they are useful in measurement of phase angle. Okay. So, we will see that they can be also used to measure a phase lag or phase difference between two AC signals. Okay. So, these instruments operate on the principle of electromagnetic induction. We have seen that in case of PMMC we were using a permanent magnets, but in this case we are mostly using the electromagnets. Okay. And they are based on the principle of electromagnetic induction. Okay. So, alternating magnetic fluxes induces eddy currents in the conducting element. We will see what is the conducting element, and the interaction between the magnetic flux which is alternating in nature and the induced current produces a deflecting torque. Basically, it induces a deflecting force which is converted to deflecting torque. Okay. So, what we have learnt is we have a alternating magnetic flux which is interact with the current, okay, and then produces a torque. Okay. We will see this in mathematical sense also, that how this current and fluxes are linked together. Okay. So, let us try to understand the principle of operation. Principle of operation of this induction instruments are very simple. They work on the principle of induction, Faraday's law of electromagnetic induction. Okay. Idea is when a conducting material is placed in a time varying magnetic field, EMF is induced as per the Faraday's law. Okay. Now, this EMF causes eddy currents to flow in the conductor. Now, the interaction between the induced eddy currents and the magnetic field which is produced results in a mechanical force. Okay. And this force produces a deflecting torque which is used for the measurement of whatever thing we are measuring, be its current or be its voltage, okay, or be its power or energy, as we have seen that they can also be used for measurement of those quantities. Okay. So, they work essentially only for alternating current, and for direct current they will simply not work. Okay. So, the induction instrument require a changing or alternating magnetic flux to induce current in the moving element. Okay. In AC circuits flux varies continuously, so alternating eddy currents are produced. Okay. In DC circuit flux are constant, so basically there is no induced EMF, and when there is no induced EMF there is basically no torque. Okay. So, that is why I initially mentioned that the induction kind of instrument are not useful for the measurement of direct quantities like DC current or DC voltage. Okay. So, they can only be used for the measurement of AC quantities. Okay. For torque to be produced in an induction instrument, the following three conditions has to be satisfied. The first condition is two alternating magnetic fluxes should be present. Okay. So, the minimum requirement of magnetic fluxes are 2. So, you will see that there are two different fluxes, phi 1 and phi 2. Fine. Then two fluxes must have a phase difference. If they are in phase, they will not produce time varying EMF. Okay. So, right now we have seen two conditions. One is there should be two alternating magnetic fluxes. Then second condition is the two fluxes must have a phase difference or phase lag between them. Okay, and the third condition is a conducting moving element should be there, and usually this conducting movement or moving element in the case of induction instrument are basically made up of mostly aluminum. Okay, without a phase difference between fluxes, there will be no net torque produced, and therefore there will be no movement. Okay, so three basic conditions in the case of induction instrument are like, first is two different alternating magnetic fluxes should be there. Okay, we'll see that there are certain arrangements that using a single coil we can generate two different fluxes, but that we'll see maybe later in this course. Okay, and then two fluxes should have a phase difference, and the third condition is a conducting moving element usually made up of aluminum should be present in the case. Okay, so let's try to understand the working principle or working of this induction instrument. Okay, in all induction instrument we have two fluxes, as we have just seen, produced by current flowing in the windings of the instrument, as you can see in the image also. Okay, so these two alternating fluxes are produced by basically two different currents. Okay, so these fluxes are alternating in nature, and they produce EMFs in a metallic disc or a drum provided for the purpose. So usually these instruments will have a metallic disc kind of arrangement, or sometime a drum kind of arrangement for these fluxes. Okay, these EMFs in turn circulate these eddy currents in the metallic disc. We have already seen that when metallic sheet or metallic drum comes into contact of these current, there will be inherent eddy current produced at the surfaces of these drums or discs. Okay, this figure shows a thin circular aluminum disc free to rotate about an axis through its center. As you can see, this is the center of this disc. Okay, now there are two different poles. This I am representing as pole P1 and this as pole P2. So there are two poles P1 and P2 producing alternating fluxes phi 1 and phi 2, which cuts this disc. Okay, any annular portion of the disc with center on the axis P1 will be linked by alternating flux phi 1, and hence it will have a induced EMF, and this induced EMF will produce an eddy current I1. Okay, so because of this flux phi 1, this eddy current I1 is generated. Okay, so I can write that the cause of this current I1 is the flux phi 1. Fine. Similarly, I can say that the flux phi 2 will be producing another eddy current, which is say I2. Okay, so this is I1 and this is I2. So I have two different alternating or say eddy currents flowing because of two alternating fluxes phi 1 and phi 2. So I can write that this I2 is flowing because of flux phi 2. Okay, so two conditions we have seen. Current I1, which is again eddy current, is flowing because of alternating flux phi 1, and another eddy current I2 is flowing because of the flux or alternating flux basically phi 2. Okay, so we have two fluxes and now we have two eddy currents. Therefore, two torques are produced. You can see that TD1 and TD2. Okay, so first flux which is interacting with eddy current is produced by the second flux, and the second flux interacting with the eddy current produced by the first flux. Okay, so you have two different conditions. Okay, so total torque is basically sum of these two torques. Okay, so let phi 1 and phi 2 be the instantaneous value of two fluxes having a say phase difference of beta. I can write that phi 1 is equal to phi m1, which is the say peak magnetic flux, into sine omega t. Okay, and phi 2 is equal to phi m2, again this is the peak magnetic flux for this phi 2, and into sine omega t minus beta, where beta was the phase difference between them. Okay, now their RMS value I can write, because both are the sine signals, I can write that phi 1 is equal to phi m1 by root 2 and phi 2 is equal to phi m2 by root 2, the RMS values. Okay, so the RMS value for this is equal to phi m1 by root 2, and for phi 2 it is phi m2 by root 2. So in place of, all right. Now flux phi 1 produces an EMF in the disk by a transformer action, okay, and the instantaneous value of this EMF can be written as E1, which is directly proportional to minus d phi 1 by dt. Okay. So, this I am calling as, say, first expression. I am not calling this a equation, this is my first expression. All right. This we will be using later on in this lecture. Okay. So, the instantaneous value of the EMF is directly proportional to minus d phi 1 by dt, the flux linkage phi 1 by dt. Okay. Now, from this expression, say, let me call this expression 1 and this as expression 2 and let it be expression 3. All right. So, from this expression 3, E1 is directly proportional to minus d phi 1 by dt, and this phi 1 value I know from my expression 1 that phi 1 is equal to phi m1 into sine omega t. All right. So, what I will do is I will put this value of phi 1 from that equation and I will get, or that expression, then E1 I will get directly proportional to minus d by dt of phi m1 into sine omega t. Okay. Or just by differentiating it, I will get that this E1 is directly proportional to omega phi m1 into cos omega t. Fine. Okay. And since omega is equal to 2 pi f, where f is the frequency, okay, E1 I can write as proportional to a value which is minus f phi m1 into cos omega t. Okay. So, it is very clear from this that E1 lags the flux by 90 degree. Okay. So, this voltage or the instantaneous EMF is lagging behind this flux, say, phi m1 by 90 degree. All right. Now, say we have seen that E1 is, say, for example, I am considering as RMS value of EMF E1. Okay. So, I can say that E1 is directly proportional to F into the RMS value of the flux, which was nothing but phi m1 by root 2. Okay. Therefore, I can say that E1 is directly proportional to F into phi 1. Phi 1 we have seen that is the RMS value of the flux. Okay. So, this I am calling as another expression. Okay. So, we have got one expression this. Okay. So, this I am calling as expression 4. All right. And this I am calling as expression 5. Okay. Now, this EMF circulates an eddy current having a RMS value of, say, I1. Okay. So, if the impedance of eddy current path is Z, I1 can be written as E1 by Z. Okay. E1 from expression 5 is given as something which is proportional to F phi 1. So, I can write that I1 is proportional to F phi 1 by Z. Okay. Now, let that I1 lags the voltage E1 by, say, angle alpha. Okay. The angle between phi 2 and I1 from the phase diagram, let us see, this is the phase diagram of this flux and the currents. Okay. The angle between phi 2 and I1 can be written as from this expression as 90 minus beta plus alpha. Let us see. So, this is phi 2. Okay. Phi 2, and say I am calling this angle, say, x. Okay. Now, this x is equal to, okay, so phi 2 and I1. Okay. So, this x, if I want to find, this is basically this 90 minus beta. Okay, because I know that this E1 and phi 1 are apart at 90 degree. So, this angle x is equal to 90 minus beta. Okay. And if I want to find the phase difference between phi 2 and I1, it will be 90 minus beta plus this alpha value. Okay, which was, we have just figured out that I1, say we have assumed that I1 is lagging behind the voltage E1 by angle alpha. Okay. So, this x plus this alpha is what the angle between phi 2 and I1 is. Okay. So the total angle is 90 minus beta plus alpha. So this is the angle between phi 2 and I1. Okay. Now the average torque produced by interaction of phi 2 and I1, the flux 2 and because of current I1 can be given as TD1, which is directly proportional to phi 2 into I1 into cos 90 minus beta plus alpha. Okay. Or it can be written as, we have assumed from expression 6 that I1 is directly proportional to f by z into phi 1. I can simply replace this value of this I1 by phi 1 into f by z. Okay. So this TD1 is directly proportional to phi 2 into phi 1 into f by z into cos 90 minus beta plus alpha. All right. I am calling this as expression 7. All right. Now, say take flux phi 2 and proceed in a similar manner. It produces an eddy EMF of RMS value like E2, which is proportional to F into phi 2, very similar to what we have seen for E1 and phi 1. Okay. Now, E2 lags the flux phi 2 by 90 degree. So E2 circulates eddy currents in the same disk. Okay. The RMS value of the eddy currents which is produced by EMF E2 is given as I2, which is directly proportional to F by Z into phi 1. Okay. Say this I am calling as expression 8. Okay. Now this current I2 lags the EMF E2 by an angle alpha. Okay. This angle. Okay. And therefore the angle between the flux phi 1, this is angle phi 1, and the current I2 is basically 90 plus beta plus alpha. Okay. So the current lags the EMF E2 by an angle alpha, and therefore the angle between flux phi 1 and current I2 is nothing but much larger than 90, which is 90 plus beta plus the alpha value. All right. So the average torque produced by the interaction of the flux phi 2 and current I2 can be given as the second torque, which is TD2, and this is proportional to phi 1 into I2 into cos 90 plus beta plus alpha. And from expression 8 we have seen that I2 is directly proportional to F by Z into phi 1. Fine. So I can write that just by replacing this I2, I can write that this TD2 is directly proportional to phi 2 phi 1 into F by Z into cos 90 plus beta plus alpha. Fine. So we have seen these two expressions of torque. This is say another expression. I am calling this expression 9. All right. So TD2 is given as phi 2 phi 1 F by Z cos 90 plus beta plus alpha, and we have also seen the expression for torque TD1, which was from expression 7 as phi 2 phi 1 F by Z cos 90 minus beta plus alpha. So these are two different torques, TD1 and TD2. All right. So we will be utilizing them to calculate the final torque. All right. So say let the positive direction of the flux be as shown over here. Okay. Assume that at the instant under consideration both fluxes are increasing. Okay. TD1 and TD2 both are increasing, and application of Lenge's law we can find that what is the direction of current I1 and current I2 as shown in this figure. Okay. Now applying the simple left hand rule, we find that the flux phi 2 which is interacting with current I1 produces a force F1, okay, which is acting from right to left, and flux phi 1 which is interacting with current I2 produces a force F2 which is acting in just opposite direction, which is from left to right. Okay. So because the two forces are acting in the opposite direction, means that they are producing two different torques TD1 and TD2 which are acting in different direction. This we have considered in the worst case. Okay. So in all the cases essentially you will get the same expression. Okay. So the total torque is basically the difference between two torques that we have just calculated from expression 7 and expression 9. Okay. So the total deflection torque TD is equal to TD1 minus TD2. All right. So the TD from the two expressions, okay, I can write that TD is equal to TD1 minus TD2. Okay. TD1 and TD2, if I put from the two expressions, I will get this TD as this TD is directly proportional to phi 2 minus phi 2 into phi 1 into f by z sin beta into cos alpha by just simplifying this. Okay. So we have found an expression, say this is expression 10, that the deflecting torque is directly proportional to phi 2 into phi 1 into f by z sin beta into cos alpha, and from this expression it is clear that the torque is directly proportional to phi 2, phi 1, it is directly proportional to f, it is also directly proportional to sin beta and cos alpha, and it is inversely proportional to the impedance path of the eddy current. Okay. So let us say for cos alpha it is directly proportional to, so TD is directly proportional to cos alpha. Okay. Now it means that for larger value of this TD, okay, cos alpha should be as large as possible, means it should approach a value say 1, okay, means that this alpha value should be as close to 0 as possible. Fine. Therefore, the path of eddy currents should be highly resistive in order that torque be large. Okay. This is also clear from this expression, TD is inversely proportional to Z. All right. Similarly, the torque is directly proportional to sin beta. Okay. Means that this angle beta should be as large as possible, means beta should be as near to 90 degree as possible in order to this deflecting torque to be large. Okay. Angle beta is the angle between two fluxes, and hence the two fluxes should be displaced by an angle like very near to 90 degree. Okay. So maximum torque is achieved when beta is 90 degree, means that when two fluxes are displaced by an angle of 90 degree or they are at a right angle to each other. Okay. So this is the basic theory behind induction type of instrument. Okay. Let us see different type of induction instruments. Okay. Induction type instruments are classified based on the method used to produce two alternating magnetic fluxes with a phase difference, which was the essential requirement for the induction instrument to work. Okay. So accordingly, there are two different type of induction instrument. First is the split phase type induction instrument, and the second is the shaded pole type induction instrument. Okay. So let us see what is the split phase type induction instrument. Okay. There are two electromagnets present here, two AC magnets basically what you call M1 and M2 as you can see here, and these are connected in series. Okay. The winding in M2 you can see that is shunted by this resistance R. Okay. I am calling this AC magnet or say electromagnet. Okay. So this winding in this M2 you can see that is shunted by this resistance R, which is very much essential in this split phase type induction instrument. Okay. The current in M2 winding lags with respect to the total line current. Okay. And this lag helps to develop the necessary phase angle between the two fluxes. Okay. In the shaded pole type induction instrument, there is only one winding to produce the flux, and the flux produced by this winding is actually split up into two fluxes having a phase difference with respect to each other. Okay. So this is constructed by making a narrow slot in the poles of the electromagnets. Okay. And a copper strip is placed around the smaller of the two areas formed by the slot, and the copper shading band act as a short circuited secondary winding. okay, because we have seen that two fluxes are required, okay. So therefore this second winding was very much required, okay. The damping mechanism, irrespective of what kind of this instrument is, as we have seen, is done by using the eddy currents, okay. So eddy currents induced in a aluminum disc or in a aluminum drum produces a damping torque which is proportional to speed, ensuring fast and stable deflection. We have seen that in not all the analog instrument this eddy current damping is possible, because many of them do not use a conducting former or even the core, okay. So in this case the eddy current damping is possible, and this damping torque is proportional to the speed, ensuring a fast and stable deflection. So TD is directly proportional to the angular velocity of the moving system, or the damping torque is basically equal to k omega, which is k is, for example, a constant, okay. So the deflection can be of course found by equating the controlling torque and the deflecting torque, but that will not be possible to discuss, because again that will require another set of discussions, okay. So I think if we understand the damping mechanism and the deflecting mechanism of this induction instrument, that will be enough for this course, okay. Then let us try to understand their application. We have in the initial part of this lecture also we have seen that the application of this induction instruments are enormous, particularly in case of energy measurements, frequency measurements, phase lag measurements, and in the power factor monitoring, okay. So mostly for the AC applications, okay. The advantage of these instruments are they are very much accurate for AC measurement, okay. They do not have much magnetic stray losses, and the construction is also very simple. You have two electromagnets and a few shunts and a small moving element which is made up of say aluminum disc, okay. The design of these instruments are also robust, okay. The disadvantage is again they cannot measure the DC, okay. They will need minimum load for their operation because of this AC signal requirement, okay. Because of the electromagnetic signals, they are very much expensive, and also these instruments are frequency dependent, because the flux phi 1 and phi 2 both depend on the frequencies, okay. So these instruments are very much frequency dependent, okay. So that's all for the induction kind of instrument. We will discuss few more kind of instrument in this week 5. Two more discussions that we have to do is the one is on the electrostatic instrument and second is on rectifier instruments, okay. We'll take them one by one in our next lectures. Thank you.